Hello and welcome back to Calculus. You already know, first, I'd like to thank all the nice people that support this channel by liking and subscribing. It helps a lot for me to make more videos for you to enjoy. Please recall, from the last video, we looked at how to integrate functions in the form of f ax plus b. Basically a composite function, but the inside function is purely linear. We said that it's a must, that it must be linear. Today, employing the rules of integration from part 15 and the knowledge of the last video, I'd like to go over how to evaluate definite integrals. In part 14, the first video on integrals in this series, we talked about integrals being split into two different categories: definite integrals and indefinite integrals. Definite integrals are the integrals which can have certain values on top and the bottom of the integral sign. And once we compute this definite integral, what we get is going to be a real value. In contrast to indefinite integrals, we don't have those values. And once you compute the integral, all you get is going to be a capital F of x plus c, and this is what we call the antiderivative function. So now going back to definite integrals and the main question, how do we actually evaluate the definite integrals? Speaking purely mathematically, we use something called the fundamental theorem of calculus. For short, as an abbreviation, some people just write FTC. Now, this theorem states that if the function f is continuous, now the word continuous means that you can draw/graph it without lifting your pen once. So if your function f is continuous on an interval from a to b, where a is less than b, and then the capital F is going to be any antiderivative of your f function, then the result that you're going to get is the following. The integral is going to be from a to b. On the bottom, we have the smaller value, and on top, we have the greater value. Hence, we had the condition that a is less than b. When you take this integral from your function f of x dx, the result you're going to get is the following. It's going to be f of b minus f of a. Please note that this here is capital F. It means you plug in your values of b and a into the antiderivative function. So here, finally, once you plug in b into the antiderivative function, and then you plug in a also into the same antiderivative function, and you subtract each other, you're going to get a real value. And that value is going to be the answer to your integral. The purely mathematical definition and theorem might seem a bit confusing. So let's use an example to break it down step by step. For the first example, we are given an integral from -1 to 0 of the function 5 times 1 minus 2x to the power of 3. So, step number 1 would be to compute this integral. Compute the antiderivative of the function. Now, employing the knowledge we got from the last video on how to integrate these kind of functions, the answer we're going to get is 5 times. Now 5 is in the front simply because it is just a coefficient. It doesn't change anything, so it remains in the front. Inside the parentheses, we are going to get 1 minus 2x to the power of 3 plus 1, which is 4. And then all of this is going to be first divided by 4, and then also it has to be divided by the derivative of the inside. Inside, we have the linear function 1 minus 2x. So its derivative is simply going to be negative 2. Now, here the good thing about definite integrals is that after computing your antiderivative function, you do not need to write the plus c. It is unnecessary. Instead of the plus c, you're going to write square brackets surrounding everything that you got. And then, on the right-hand side of the brackets, you're going to put your lower bound and upper bound. Now, one thing I'd like to note is that there may be different notation used. Some people might use the square brackets and put the bounds on the right-hand side. Others might just write a straight line on the right-hand side and then put the values from -1 to 0 on the right-hand side of this vertical line. Both these notations mean the same thing. Okay, so now that we have done that, the next step is going to be plugging in your boundaries into the antiderivative function. From the fundamental theorem of calculus, we see that we first plug in b. It means we first are going to plug in the upper value or the greater value. In our case, the first thing we're going to have to plug in instead of x is going to be 0. Okay, then we're going to put the minus sign, and after that, we plug in a into the antiderivative function. In our case, the lower value, so -1. And then finally, all you have to do is just calculate everything. You can do this on your own, and I can tell you the answer here is going to be just 50. I believe this isn't extremely difficult. So let's take a look at one more example that has something to do with trigonometric functions. Here we are asked to evaluate the integral from 0 to pi of the function cosine of 1 over 3 times x. So, once again, the first step that we have to do is to compute the antiderivative of cosine 1/3 x. The result we're going to get is sine of 1 over 3x and then divided by 1 over 3. So, if you were to simplify this, all you're going to get is 3 sine of 1 over 3 x. Then you put your square brackets, and on the right-hand side, you write your lower and upper bounds. After that, first you have to plug in the upper bound. So we get 3 sine of pi over 3 minus 3 sine 1/3 times 0. This right here is basically 3 sine of 0, and we know sine of 0 is just 0, so this entire part just becomes 0. Here in the front, we have 3 times sine of pi over 3. We know that sine of pi over 3 is going to be square root of 3 over 2, and then all we have to do is multiply another 3 in front. So the final answer we're going to get is 3 square root 3 divided by 2. Perfect. Now that you know how to do this, to end this video, I would like to go over a few properties of definite integrals. I can tell you immediately that some of them are going to be the same as we covered in part 15. For example, this property here simply states that if you have a coefficient inside multiplied with the f function and you're taking the integral of it, the coefficient k can just go in front. The next property states that if you're taking the definite integral of one function added or subtracted with another function, you can simply rewrite this integral into two separate ones. Now, the following three properties are going to be new. Now, if you're taking the integral of a function f of x, from A to B, there's actually something you can do. You can flip these values. It means you can now take an integral from B to A of the function f of x dx. However, there's one thing you have to add in front, and that would be a negative sign. The next property is probably a rare case. However, it's stated to tell you what happens if you're taking the definite integral from a to a of a function. Now note here that a and a are basically the same number. So if integrals are meant to find the area between two different intervals, two different x values, but you're taking the integral from the same value to the same value, it means there is no area. So all you're going to get is 0. Now finally, the fifth property is probably going to be the most widely used definite integral property, especially when we start exploring how to actually find area. Here it states, if you're taking the definite integral from a to a value c of the function, and then you add another integral from that same c to the final value b, you can actually rewrite this into one integral from a to b of our function f of x dx. However, here there must be a prerequisite. The prerequisite is the following. A must be less than C, and C must be less than B. This fifth property right here is quite important and will be used a lot later on, and I will make sure to show you when we do. So for now, that's it for today. In the next video, we're going to start looking at integrating techniques, because the previous two videos were simply the basic rules of integration. Next up, we're going to look at the more interesting and complicated function and try to integrate them. So, I hope to see you there and have a nice day. Bye!